This is a supplemental lecture intended to help students prepare for their final project, particularly the portion that's due on Thursday, translation of the code from C to MIPS to binary in order to actually run their project. So this is an example set of code that I've come up with here, and this is based on two assumptions. It's the same assumptions that you'll be using in your final project. You have 32-bit instructions, so every time you have to do the PC +4 and shift left 2 for branch and jump type instructions. However, we will be using an 8-bit byte addressable data memory. So instead of incrementing by 4, doing the shift left logical in order to do load and store operations for when we're using variables, you're only going to be incrementing by 1. So it makes this code a lot easier, particularly here. This particular line of code will be easier. So the first things first, we have to actually we're going to be going into the data memory, and we're going to be putting these values here, because we recall MIPS is a load store architecture. Things are loaded from the data memory and put into the registers. The registers are not initialized themselves. So what's happening is we're going to start with this first instruction, int I. We're starting in main. Value of 0 is going to be 2 because int I. So here we're going to we put the tab in. Remember, because we have 8-bit byte addressable data memory. Now, if it was a 32-bit value, the next value would have to be 4 in your DataMemory.txt file. However, because it's only an 8-bit byte addressable memory, you're not incrementing by 4, you're incrementing by 1. And the next result, we're going to have j, so j is going to be 0. Now we're initializing vowels, this array here. So it's important to note that the base address of the array physically is going to be 2, and the first value in the array is going to be 1 here. Next, val is 1. We're going to increment by 1 and put the value 2 in there. So the actual physical address is 3 in data memory. It's the second value of the array, and the actual physical value is 2. Next, we increment by 1. We go to vals 3. The physical value of vals 2 is 3. And then physical value in data memory is 5. Vals 3 is 5 here. So this becomes 101. And these are the values that are actually stored in your DataMemory.txt file. So the next step is taking all of this and coming up with your InstructionMemory.txt file, which we currently have blank. So the first step is to determine the assembly language. So our first step is we have to, since it's a load store operation, we're going to do load, and we're going to initialize S0 to I, and then we're going to have 0 offset. So we're going to call S0 is I. So here's what's physically happening. If we go into our actual MIPS data path, we are getting the instruction memory, going to the control unit. 25 to 21, we're going to register 0 because that's where our base address is, and we're going to go off here. Now, the value 0, because we just want the first value, is stored in 15 to 0. We sign extended 16 bits. We go here. Our controller selects ALU sources 1 and puts that value to the ALU. These values are added and put into the adder. Now, it's important to note that this goes around here, so we're going to have this for the time being. It gets the physical value from the data memory. If you recall, that physical value is this value right here, 0. It's getting this value. The actual value is 2. That's being put out here on the read data. So it goes to read data here. So now we have values from ALU and the data memory coming to this multiplexer. We want this one, right? So we're going to select the value 1, and it's going to come back, and it's going to be physically loaded into write data. Now the write register, we're going to take 20 to 16, so it's going to be 0. In this instruction, is S0. So that's what's physically going on in that data path at that given moment. So the next thing we need to do is we need to get the value of J. Now J, physically in data memory, is 1 here. So 1, load word, S1, we're going to call S1 as J, and we're just going to have 1 here, pound 0. Now again, we don't increment by 4 because of the 8-bit byte addressable data memory. So we're just going to the next block. If it's a 32-bit byte addressable data memory, like you have in the data path presented in class, you have to increment by 4. So next thing we need to do is we need to actually get the base pointer to the memory item here in a register. Remember, we're not going to be loading all of these values from the data memory. We're going to be taking advantage of the principle of locality by just loading a value into a register. So we're going to call it S2, right? But it's not in data memory, is it? The actual values are in data memory, but this is a pointer created by the ALU, so we're not doing it on the allowed word. What we're going to be doing is we're going to do add I, S2, we're going to do 0, and 2. So S2 is base pointer to vowels, and that's equal to the numerical value of 2. So next thing we got to do is we now have the base pointer accounted for, right? And the base pointer, by using a load, store, and the offset, we can now get to all of these. So now we have access to all of the functions, with all of the actual values of the data through instructions. So next thing we're doing is we're actually calling this function. So we have to go in order that the coder dictated. And if we recall from the MIPS screen sheet, we actually have 4 registers, 4 through 7, are indicated as function arguments. And it says specifically, preserve the cost to call, no. So we actually have to get the values from these registers, these local registers, the saved registers, and put them into the function call. So we're going to add I. It's going to be A0 because it's our first function call in the function. And then we're going to put the base pointer, which is S2 here, S2 and 0. We'll call A0 is base pointer to vowels. Now since we're just 2 plus 0 is 2, so therefore again it's actually equal to 2. So 4, we have to do 1. So here's where it gets interesting. We now have a pointer to I. We're passing by reference. We're not passing by value. Here we're passing by reference because we're passing the base pointer, right? If we go to I, we recall that I is found here in data memory at 0. So what we need to do is we need to put the pointer to the location in data memory, not the physical value itself, right? So A1 is going to be at I, and then we have 0 and 0. A1 is pointer to I. A1 does not contain this value. It contains 0 here. That's the difference between a pointer. So 5. Now we're going to do J. Well, J is the actual passing by reference. So that's going to be A2. And it's going to be what? S1 and 0. A2 is value of J. And since we've loaded that, it becomes 0 here. We came here. 0 plus 1. Get that value, and that's stored in S1. So now we have S1, we add the value of 0 plus 0 is now A2. Right? So we have to do one more thing. So we've indicated these values here. And we know that next thing we're going to do is we're going to jump from here to the function. But we have to have one other thing. We have to initialize an RA, our return address. So if we're going to have this function where we're indicating it, 7 where we're jumping, and then 8 is going to be our next instruction. We're going to have add I, JR, 0, and 8. Now, I want to note that when we're using add I, we're not using these pseudo instruction sets. We would try to use some sort of value for move or load immediate if it was a pseudo instruction. But that's not what we're going to do, because I'm not allowing on the exam or in projects the use of pseudo instructions. So we're doing add I, JR, 0, and 8. So 7, we're going to be jumping. Now here's the thing. We don't know where the instruction is going to begin yet because we have instructions afterwards that we're going to be taking care of. So we're just going to call it while function. In the meantime, until we get it, then we can replace that. So here at 8, we're going to be getting a return value from the function, right? We're going to be getting an integer that we're going to be putting into J. So if we recall, V0 is a value for function results. So what we're going to do is we're just going to have V0 plus 0 is equal to the new value of J. So add. We're going to put the value into J, so this is S1. And we're going to have V0 and 0. You can also do this. You can also do 0 and change it to an add immediate. Both are perfectly correct. Let's just change it to this for the time being. So now we're up to 9. See, we're adding J equals J plus I. Now notice how, again, we passed it by reference, which means the value in data memory will be changed. And when we go through the actual implementation of the code later, you'll actually get to see how that happens in data memory. This means we have to do the same load word instruction to get I again, right? So now we've updated it after our function call. We get I. And now function 10 is just going to be J equals J plus I. So we add S1, S1, and S0. And then lastly, 11, we're going to call this JR pound 0 because of return 0. Now, there's one other thing we can do here. It's important. Remember, recall that it's a load and store architecture for I and J. So one thing we actually need to do here is we actually need to do 12, and we'll call this store word. Store I into data memory. And then 13, oh, so this is 11, and that's 12. And that's store word, and then we got to store J. And this becomes 13. So this would now be where while function is, right? So this becomes 14. So what we can do is we can immediately change this to 14. And then we start here. So the first thing we have to do is we're now doing this. So we're doing while vals J is first. So we have to get the value from the data memory offset by a variable. Now, if this were if this was a 32-bit byte addressable data memory, we'd have to do the following. We have to do shift left logical T0 A1, A2, because that's J, and then 2 to get J times 4, right? Because that's what we have to increment to find that next value. But here's the thing, it's only an 8-bit byte addressable memory. So we're only going to go to the value of j itself, right? So we don't need to do this anymore. We just do add T0, and we have to add the base pointer of vowels, which we have stored in A0. And then we add j, because that's the number of blocks we go by. So j is going to be A2. So then we go to instruction 15, and then we're going to load from data memory the value of vowels. We're going to call this T0 again for reuse, 0 T0, and that's going to be T0 is equal to vowels of j. Now 16, we have to recall that we're passing I by reference, not by value. So we actually have to get the value from the data memory, right? So we're going to do a load word. T1, we'll call this a temporary register. We'll call it 0, A1, because A1, as you recall, is the pointer to I. So what's physically happening is instead of getting a copy from the registers, this allows us to get the value from the data memory, load it here in a temporary register, and then every time we update it, we just calculate where the address is, right? And then the actual physical value is going to come from here and be written to the data memory. So now we want to do our comparison. We have a while function here. While vowels j does not equal I. So what do? If it's not equal, that means we want to do the code, right? That means we want to branch if equal. It's the opposite. T0, T1, and let's just call this end while for the time being, because we have yet to calculate our actual location. 18. First thing we're going to do is go to star I++. So we're going to do add I, T1, T1, 1. Now, remember, it is a pass by reference, not pass by value. So that means we have to immediately do a store word operation. We have to do T1, 0, A1. Before we can do anything else. So we maintain that cache consistency. Next, we do add I, A2, A2 and 1. So this is J++. This is star I++. Value in data memory. So now what do we have? Now we're at the end of the loop. We want to, 21, do what? Jump back here. So we want to jump back to the initial value here, where we start. So this would be jump 14. So now we're out of the loop. So here's the thing. We're now doing this vowels j, where we're going to update the value of v0, which we're going to be taking up here to put into j. Now, this is an important point about this code. So, vowels j is compared, it's in the temporary register, and it'll be here. The only way that the value of j is incremented is if we go into the loop. If we go into the loop, we do the comparison again. So if branch equivalent is such that we're actually going to go to instruction 22, that means the value of j is not updated, which means we don't have to do this because we already have values of j in our temporary register. We're going to have it here. It's not been changed. The only way this would change is if we immediately jump back up to 14. So if we are here, that means that we've branched past the add I, and therefore this value of t0 is the same, which means we do not have to perform a load and store operation again. So what we're going to do immediately is perform an add operation, because we're going to be adding t0 plus 2. So we're going to do add I, v0, t0, and 2. So now we have it stored in there, so that way when we jump back here, we're going to be jumping back to this instruction. And as you recall, we stored the value of 8 into JR. So the last thing we're going to do is we're going to do JR RA. So it goes to register 31, gets the value 8, and goes here. And then we'll take this value in V0, change it to I, and then we finish the code. So the last thing we need to do is we need to change this end while. Remember, we have PC plus 1, right? So we're going to be incrementing our code. Goes to 18, right? 18. We want to get to 22 minus 17 minus 1. So that becomes 18, so that's 4. So that becomes our value of 4. So now we have our entire assembly language function to do this code. So next thing we have to do is we now have to get the binary values. The binary values come from changing this and putting it into the instruction memory. So the first thing we need to do is do 0. We do load word, S0, 0, and 0. So if we go to our MIPS screen sheet, we look at load word. You know, load word is 23 hex, so our opcode is 100011, right? RS, this value is 0, so it's going to be 5 zeros, 1, 2, 3, 4, 5. RT is S0, so if we go here again, we know that it's 16, so that becomes 1, 2, 3, 4, 5. And then we have 16 bits left, which is the value of what? 0. So it becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1. Load word again, so we know it's 1, 0, 0, 1, 1. S1, right? But RS is 0, so it becomes 1, 2, 3, 4, 5. And 16 is S1. RT is S1, so it becomes 1, 4, 5, because that becomes 17. So we go here, 16 is S0, therefore 17 is S1. And then it's an offset of 1, because that's this one. So here, the next 4 instructions are all add I instructions. So instruction 2, we go here, we see add I. Opcode is 8 hex, so that's 001000. So that's our opcode. So what are our instructions? RS is 0. RT is S2, so that's 18. And then our add I is 2. Three, 0010000, because we already know that from add I. Now we have S2 plus 0 is A0, so RS is S2, which is 18, right? A0 is our destination, or RT. A0 is 4, so this becomes 00100, so that's where we're storing it. and then 0. Instruction 4, it's an add I again, 0, 0, 1, 0, 0, 0. And then we're going to take the value from S1, right, which is 16, 15, 1, 0, 0, 0, 1, so that's 15. I'm sorry, that's 0, my fault. I'm looking at instruction ahead. 5 zeros there for 0. A1 is 5, 0, 0, 1, 0, 1. And then it's all zeros from here because we're adding this one. And last but certainly not least, well, we have 2 more. 0, 0, 1, 0, 0, 0 for add I. So it's S1, so it's 6, 15, A2, which is 6, and then zeros. Instruction 6. One more time with add I. It's going to take 0 here. JR, which we know is 31. We'll go by going to our MIPS screen sheet. JRRA is 31. That should be RA. And then we're putting in 8. Seven is a jump instruction. 7, we go to our MIPS screen sheet, we look for jump. 2 hex, so this becomes 0, 0, 0, 0, 1, 0. And then it's going to jump to 14. So we know that 14 is 8, 12, right? So that's 8, 12, 4, 0. There we go, 14. And then we just add the rest of zeros till we get there. 8, we're going to do add. Now we know add, our opcode is going to be 0 because it's 0 for all R types. Function, the last 6 bits is going to be 1, 0, 0, 0, 0, 0. So let's do the first 6 bits. S1 is, we're first adding 1, 0, 0, 0, 1. And then we're adding S0. So I'm looking at the wrong one. SV0 is our first one that we're adding. V0 here. We go to 2, 0, 0, 0, 1, 0. So that's V0. And then we're adding RT, actual value of 0. And then for S1, for 17. And then shift amount is 0 because we're not shifting in this instruction. And then last but certainly not least, 2, 0 for our opcode, 1, 0, 0, 0, 0, 0. 9, we're going to do load word instruction again. Start out with load word, so that makes life easy here. In fact, if you notice, it's the entire instruction again. So we can just copy and paste. Add, we know that it's 2, 3, 4, 5, 6 for 0 for opcode. Then we're adding in instruction 10, S1, 1, 0, 0, 0, 1, plus S0, 1, 0, 0, 0, 0, equals S1, 1, 0, 0, 0, 1. No shifting, so we have 5 zeros. And then 2, 0 for the function. 11, we're going to do store word. Now, store word, every bit after this is the same, right? Let's see. S store word, we're going to take the value from RS, the sign immediate equals RT. So store word, our opcode, is 2B hex. So 2, and then B becomes 10, 11, right? 8, 10, 11. That's 2B hex. And then RS is going to be, we're to instruction 11, 0. RT is S0. So that's 16. Right? and then the rest of it for instruction 11 is 0. 12, store word, we have the exact same 101011 for 2B hex, and then we're going to have RS is 0 again. Store word is 10001 because that is this value here. And then again, because we're incrementing the offset of 0, we are here. 13, this is where we go here for jump register 0. JR, jump register 0 and 8 hex. 1, 2, 3, 4, 5, 6. And if we look at the register transfer language, you see that P is C is equal to RS. So we're going to take the value from RS and encode to the program counter. So to answer a question that was asked last lecture, how do we do this? How would we modify this data path? So what this instruction is saying is we're going to go here, we're going to get RA, which is 31, and it's going to come out here. So what we're going to do is it's going to go around the ALU, it's going to come over here, and we're going to use, you create another jump register, and we use that using the controller to go back to the program counter. And the other input would be this one. I'm sorry, this would, yeah, so you have 0 and 1, where this would be this one, and 0 would be this one, the control signal would hold that. Now it's an R-type instruction, so what's going to do is it's going to send a value to the ALU controller, and the ALU controller is going to generate this control signal. So going back to our original code, so we have our code, and we're going to have our instruction memory. This means that if we go to jump register, RS is going to be 31. RT is a don't care, so we're just going to call it 0. I mean RS, RT, and RD is a don't care. Shift amount is a don't care. And then the last bits are going here, jump register 08 hex. So this becomes 001000. So that's our jump register. So that's how return 0 actually works. For instruction 14, we're now going to take RS, where we have our add instruction. So we recall instruction 10, our opcode is all zeros again. RS is going to be A0, which is 4. RT is going to be A2, 00110. And then RD is going to be our temporary, so that's T0, so that's going to be 8. Because as you recall, T0 is 8. So shift amount is going to be 0, because this is an R-type instruction. And since it's an add, it's going to be 100000, since it's 20 hex for the function. For 15, we load word. We already have load word is 23 hex, so we can just make that 23 hex, right? Load word, RS is T0, so that's going to be 8. RT is going to be also T0. And then our offset is going to be 0. 16 is going to be load word, so we have 100011. It's going to be 0 of A1, so RS is going to be A1, which since we have A0 is 4, that means A1 is going to be 5. It's going to be 00101. RT is going to be T of 1, so that's going to be 01001, so that's 9. And it's going to be all zeros for our immediate value. For 17, we're going to do branch equivalent. Branch equivalent is an I-type instruction. Branch on equal, opcode is 4 hex, so it becomes 000100. RS is going to be T0, so that becomes 801000. RT is going to be T1, so it's going to be 0, 1, 0, 0, 1. And then our actual branch value is going to be 4. Now we're actually going to be doing the inside the loop. So our immediate opcode, as we know, is 8 hex, 0, 0, 1, 0, 0, 0. RS is going to be T1, 0, 1, 0, 0, 1. And then RT is going to be 0, 1, 0, 0, 1. And then it's going to be all ones for our increment. So 19, we now need to do this load operation, the store operation. So if we go to store word, we scroll from instruction 11 to be hex, store word. RS is A1, so that's going to be 5, 0, 0, 1, 0, 1. RT is T1, so that's going to be 0, 1, 0, 0, 1, so that's going to be 9. And then the offset is all zeros. So 20 is add I. We did add I in instruction 18. So that's our function is 8 hex. And our opcode is 8 hex. And RS is A2. So it's going to be 0, 0, 1, 0, 1. So that's 5. I'm sorry, 6. A2 again for RT. And then it's going to be add 1 to J. And then instruction 21 is going to be jump. Jump. Our opcode was 2 hex, so it's going to be 0, 0, 0, 0, 1, 0. And then guess what? It's going to be 14. It's not going to be 14. We're going to jump. Oh, it's going to be jump 14. That's going to be the same thing. So it's going to be 14. So guess what? It's actually going to be the exact same binary instruction as this. And that is our opcode, and that's our jump address. 22, we're going to do add I again. So add I from 20, it's going to be 8 hex, 0, 0, 1, 0, 0, 0. RS is going to be T0, so that's 8. RT is going to be V0, which is recall from here is going to be 2. And then RD is not existent because it's add I. So it's going to be 2 here. So we're going to go all the way here, and that's going to be 2. Last but certainly not least, 23. We recall from jump register in instruction 13. It's an R-type instruction, so it's going to be 0. RS is going to be return address. That's 31. I probably should have made a mistake. You guys have probably noticed it while watching the video. Instead of RA, it should be 0. And then the rest of this, these bits are 0. These bits are 0. These are don't care, so we're down to the last 6. And if we look at instruction 14, actually let's do better habits and look at the MIPS screen sheet. Jump register, 0, 8 hex for the final, so 0, 0, 1, 0, 0, 0. So there is our set of actual binary values. So the question is, now that we have our assembly language, and we understand the register transfer language, and we have our InstructionMemory.txt, we have our DataMemory.txt, now we can actually see what's physically going on in the data path. So here's what's going on. We start at instruction 0. Now this is a load word, right? So we're going to load this value. So you separate this out. We're going to do load word, and then we're going to go get this value in our offset. So what's physically going on is a load word operation. We're getting from R1, and we're getting the value from R1 and putting it into the ALU. Then we are also taking RT and putting that value here to wait to write to it. So the value that we're writing to is here, right? So if we have these values, we look back in the instruction, load word 0, S0, right? So that's a register we're getting the value from. We're writing it to S0, which is this, and then we're adding the value in 0 plus this to the actual data path. So what we're doing here is we're taking the value 0, the immediate, adding it. This should go here. And this comes out. We add and calculate the address. The address obtains that value from data memory. Now the value from data memory in DataMemory.txt is actually this value here. So it gets that value from the data memory, puts it out here, mem to reg becomes 1, and then it is loaded into this register indicated by RT. So that's the first instruction. Second instruction, we're doing another load word. So we're doing 0 again. We're getting 0 here. 0 here. This value here is going to be S1, so we're waiting for S1. 0 plus 0 is 0. Get the value. Get the value from data memory. 0 plus 1. It gives us 0 plus 1, so we're actually getting this value from the data memory. That value comes out and goes here as indicated by S1. Instruction 2, 00100, is going to be, as you recall, an add-I instruction. So it's actually going on here. We're getting this value here. 25, 21 comes out. 20 to 16 is the add-I, indicates where we're going to write. The immediate value, the last 16 bits, is sign extended and is put here again. Comes out here. Now, since it's an add-I, it's going to come around, go through the 0 portion of mem to reg, and get stored into the registers here. The next instruction is, again, add-I. So this is A0, S2, and 0. So that's this value here, right? So for 3, what we're going to do is we're going to get the value from instruction memory, goes to control unit again. We're going to tell which one to write it to. And then we get the immediate value. Comes through here, it's calculated, added, comes through here, comes through there. Again, 4, right? Add-I, take the value from 0. This one's going to take the value from 5. If we look back here, we can do 5 and go, that's an argument value. So now we're loading the arguments into the function. Again, add-I, RS, we get our control unit, selects reg destination, our immediate value is added, the value comes from the registers, comes out, circumvents add, and comes through here. Stored into write data and is indicated by the address indicated there. We do this 2 more times with 5 and 6. And if we look at 5 and 6, we are now indicating here what value is going to go into the A2. A2, as you recall, is an argument. And then the last instruction, we're updating the return address for 0 and 8. Right? We're getting the value from register 0. We're incrementing 8 from the immediate, and we're putting it in register RA. So jump 14 is instruction 7, so it's going to go here, 2 hex. So this jump instruction is going to increment the instruction. PC plus 4, we need to keep that because why? This is a good question. Remember, we have our assumption here, 32-bit instructions, 8-bit byte addressable data memory. So we have to increment the instructions by 4. So since you guys weren't here to correct me, $48, $52, that makes this one $56, that one makes this one $60, $64, $68, $72, $76, $80, $84, $88, and $92. Going back here, we're doing a jump instruction, so that makes this here. Now also remember from the instruction memory, you have 25 to 0. That's 25 to 0, and 7, which 7 times 4 is 28, so you can see this value is here. That's going to be 14. So that's actually shifted left by 2. We concatenate. Jump becomes 1. So we select this value. Branch is going to be 0, so we select this value. And it comes all the way back around to the next program counter. Now, since we go to 14, 14 times 4 is 1656, right? We're going here. So this is what we're doing. We're now doing our function, right? And we now know that this value here, the last value of the function, by updating this value to 8, will bring us to 8 times 4 is 32, so we'll go here to this instruction. So that's what's physically going on in the instruction memory. The jump permits us to go from 7 times 4 is 28, multiply by 4, PC plus 4, takes us all the way out to 14 times 4 is 56. So this is where our function begins, and that's where our function ends. So now we're at function 56. So now 56 takes us to here. 14, we're going to start by taking the value from the base address here of A0, which is vals, adding J. And the reason why I don't have to do J plus 4 is because it's an 8-bit addressable memory. So we do this. We're going to get the value of J, which comes through here. So 25 to 21 comes through here. Gets it, adds it, calculate our address, right? And we get the value from the load word to come here. So the next instruction, right? Doing 2 load word instructions. And then we get to our branch. So we've already done 14 and 15. So we're updating local copies of registers, right? So we do a branch instruction. Now what the branch is physically doing here is it takes the values from here and here, these 2 registers, right? So we know that the registers, the instruction that we're doing, BQ, T0, T1, and 4. Now if we go to instruction 17 and go to our instruction memory, 17 times 4 is 28, that's 68. So that's this instruction here. So what's going on here is this is our branch, and then we're comparing this register with this register. And then if the branch is equal, we go to this particular instruction, right? Plus 4 in this case. So here's what that means. We could do the comparison, right? The comparison comes here, comparison comes through here, ALU source is 0. I do the comparison and it comes here. And they also have a branch. Now there's also our immediate value. goes past here, gets multiplied by 4, shift left 2, because we still have to account for that 32-bit instruction. We have PC plus 4 here, right? And then it's added. So this is the value we want. So with branch here, select this value. So it's going to take this value here, and we branch if that's the value we want. So let's actually see what's physically going on when we do this comparison. The value is actually at this moment, so we're in our first iteration, so j is equal to 0. So we've added 0 to AI. So the value of t0 is vals of 0. So we've loaded 1 here. So when we go to the registers, the first value coming out is 1 from this particular instruction. So the value coming from this register is 1. So what about this value? So this value means we're comparing it with star I. So now we have temp register. Well, we've loaded it from the memory, so it's 2. So 1 and 2 come out here, right? 1 comes here, and 2 is here. So it's going to happen. So we have a branch instruction, but it's going to say 0 and 1, which means 0 is going to come here, and we will get this one on the first iteration. So that means we're actually going to go into the branch. So next thing we're going to do is we're going to increment I. So we're going to increment ti, right? And this is pretty straightforward. We're going to add I plus 1. And then it's going to come out of the ALU, come around, and then it's going to update ti of 1. T1, I'm sorry, not ti. Now here's the thing. It's the pointer to I, not the actual physical value of I. So we're going to perform a store word operation. So what's going to happen next is we're going to get this value here. This is our location in memory. We have our offset, so it's 0 and 0, or I'm sorry, this is A1 and 0, and this adds 1. Now, we're going to get that value we just updated in T1 here, and that's going to come from R2 and go here, right? So that's going to increment 2 to 3. So this is actually going here into our data memory and updating it plus 1. So now it's going to become 3. So that's what's physically going on when you have a pointer. You're physically updating the value in data memory. And then J is incremented. We're going to update it here. We have J, we have 1, right? And that's going to come out here and be updated in the register. And then J is also duplicated, so we update it here. But here's the thing. You notice how we haven't updated in data memory, and we're only using these values, these registers from the arguments. We're not actually updating the value of J. So we haven't updated the value of J in the function, which is S0, it's S1, and we have not updated the value in data memory. So that's why when you pass by value, you lose the value of that variable the moment you jump out of the function. Because as you see from our actual compiled values, when we jump out and we go back here, we're using S1. So it's overwritten. We don't care. We don't care about A0 when we're not in the function. We're in main. So for the first time, we've updated this to 3. So we've incremented, so this becomes vals of 1. So it's going to make the comparison. Is vals of 1 equal to I? So it does the load again. So vals of 1 is this value 2. Is it equal to 3? No. So it goes in there, increments I, performs a store word operation. When we perform the store word operation, it becomes 4. Increments J to 2, the local copy. So increments J to 2, it performs the load word from J, gets this copy, this value here. It's 3. And then it performs the load word to get I, 0. Is 4 equal to 3? No. So therefore, we're going to do the value inside the loop. We increment I, update the temporary register. Then we perform a store word operation. So this becomes 5. Right? So now we've updated it. We increment J to be 3. We perform a store word operation to get the values of 3. We go to values of 3 and we get this value. We perform a load operation to get this value from the memory. They compare. Branch if equal. Well, now they're equal. 5 is equal to 5. So here's what's going to happen. We're actually going to branch past these instructions. We're going to branch PC plus 1, 2, 3, 4. We have plus 1 comes here. 2, 2, 3, 4. So now we're at this instruction, at add I. So now we're able to leave the loop. We're able to leave the loop. What we do here is we go to the data path. We're going to update RS and V0. Right? We're going to perform an add operation, right? We go back here, we take a look at our code. Add I, T0 and 2. So we have V0 is going to be here, T0 is going to be this one, and then we're going to have 2 come here. So T0 is going to be here, V0 is going to be here, and then 2 is going to actually be here. Add them up. We don't go there because it's an add I. We circumvent it, and then we store it in V0. The last thing we're going to do is we are going to jump register again. So we go here, we get JR, we get the value from the register, branches out, go to the controller, it's all zeros, but it sends the function to the ALU control, which generates our control signal, which selects the physical value here to go back to the program counter. Now if we go to our assembly language, here it's an RA. RA we stored earlier as 8, so we go back to this instruction. So then we have V0 here, so we have the value from the register, and we're going to overwrite J. Right? S1 is J, because here J is equal to V functions. The result is stored in V0, and we're just going to add 0 to it because we want this actual value in J. Now, I mentioned earlier you can do add I0, that's perfectly fine. So here's what's going to happen. We're going to take the value from the result of the function, that's going to be here. We're also going to add 0 from the function 0. We'll put that out. We add them. And then we're going to store it into J. So that means these two values, there's this here, plus some 0, is going to be put into this physical copy of the variable. So then last but certainly not least, we're going to increment J plus I. If you recall, in order to get this value, we actually have to do a load word operation after we jump back, right? Because we actually have to get the copy from the register because we passed it by reference. I'm sorry, a copy from data memory. So we're going to go to here, we're going to get the address. We're going to get this physical value. And when we go to the data memory, we're going to notice that it's now 5. When we passed it there, it was 2. That allows us to pass by reference. So the value of 5 is now right here. And put into the registers. And then the last thing we're going to do is we're going to do 5 plus vals of J plus I, which we return from 4. values of j was 5, so it's 5 plus 2 is 7. So we're going to add 7 plus 5, and the final value of j is going to be 12. So the last thing we're going to do is we're going to take these values here, and we're going to perform store operations. From these two store operations, we're going to get I and j. So the first thing we're going to do is we're going to get store, go get I, the address of I, which we know is 0. Offset of 0 is here, so we calculate this address. And then what we're doing is we're actually getting this value of I and putting it here. Now we're physically overwriting it, and we'd be writing the value of 5 there. Now j started out as 0, but j is now 12 in that value of S1. So what we're going to do is we're going to, again, store here. By calculating the address, we're adding 1 to this address. And so the value we're getting from the registers comes from here. It's now 12. That's now going to be stored into data memory. And then what's going to happen here is the actual value, we've calculated 0 plus 1, so that becomes 1. So now the value we're storing in there is 12. 8, 12, 0, 0. And then the last thing we're doing in the function is JR0. So that allows us to jump back to 0, and the program will be over. And so that is how that's taken care of.